Uncorrected. I'm happy to introduce to you today Julia Signell. You may recognize her last name because she's the daughter of Rich Signell, who works here at USGS. Julia is entering her senior year at Smith College this fall and in environmental engineering. And we were very lucky to have her work with us this summer through the Smith Praxis program. Julia was such a pleasure to work with. We're really going to miss her and her great work that she did when she was here. I don't think she realized that she was signing up for schlepping lots of heavy gear over salt marshes and getting really muddy and bugs everywhere, and she never complained once. She was a lot of fun, and so we're really going to miss her. And today she's just going to summarize some of the work she did as a component of this larger salt marsh project that we're doing in collaboration with Lindner and MDL, looking at a new CO2, continuous CO2 sensor measures CO2 fluxes in salt marshes. So with that, I'll hand it over to Julia.
Alright, so I was focusing mostly on the data analysis side of calibrating the CO2 sensor. So the whole idea behind this project is that the carbon market has been focusing primarily on forests, but estuaries are actually a much more efficient sink of CO2. They're a much smaller percent of the total land cover of the world, but they have about 5 times as much capability to absorb CO2. This is just an idea of how they compare. We really aren't sure yet. This is a number that Kevin gave me, which might be easy to wrap your head around. 50 to 150 grams per meter square per year of carbon can be absorbed by estuaries. This is part of a bigger project to quantify greenhouse gases and carbon flux in and out of wetlands. So we've got the vertical fluxes here, this diagram of CO2. This study in particular didn't focus on that. There's other people at MDL doing that. But we did the lateral fluxes, which are, so the vertical fluxes are evapotranspiration, but the lateral fluxes come from when the salt marshes flood. That brings in carbon pore water from the ocean, and then it fills the pore water space, and absorbs metabolic CO2. Then when it drains back out, it is a net source of carbon to the estuary. So the primary source of carbon to the wetlands is vertical, and then it sends it out into the ocean. So we're only looking at the lateral fluxes of particulate organic carbon, dissolved organic carbon, and dissolved inorganic carbon. This is just a schematic of how, when it floods, it comes in, flows the pore water, and goes back out as really rich concentrated CO2. We also were looking at nitrous oxide and methane, just because those are really important greenhouse gases. So this is just a diagram that Neil and Kevin put together for a proposal, just to show the importance of continuous monitoring of carbon. This shows DOC across a week, and this is a neap tide. This is a spring tide. So you can see that if you take the DOC from a neap tide and extrapolate for a full year, which is not a reasonable thing to do, but just as an example, you would get that it's 3 grams per meter square per year of export, whereas if you took a spring tide, you get 39 grams per meter square per year, whereas in reality it's probably more like 18. So you have to be really careful about doing these tidal efforts where you just look at discrete samples over just one tidal cycle, because you can get results that are very skewed that you wouldn't be able to see if you just zoom in really close. We're going to look at this here. So this is DOC, and this is DIC. So, and this DIC is in the green, DOC is in the red, and the POC is this kind of flat black line here. So this is just showing what an important part DIC plays relative to other types of carbon in the system. I mainly focus on DIC. And specifically within DIC, which is dissolved inorganic carbon. I don't know if I did that. You can see that there's this relationship between the form that the inorganic carbon takes and the pH level of the water. So when the water is very acidic, all the inorganic carbon is as CO2 or carbonic acid. Carbonic acid is very small compared to CO2. And then as the pH increases, more of it goes as bicarbonate up until it gets very basic, and then it goes mostly as carbonate. So we were looking mostly around a pH of 8 for seawater. So we were measuring CO2 when it was a very small percentage of the total dissolved inorganic carbon. We did this because you can measure CO2. So there's this idea that even if the error of the CO2 is small here, and when you scale up to DIC, it gets extrapolated, it gets increased by a lot, it still might be an important number to have that DIC. So these are the sites that we take. Great Pond is our high nutrient site, so there's a lot of anthropogenic load. And then Hamlin Pond is our mid-nutrient, and Sage Pond is at the Fort Site. That's a reserve, so it's very low nutrient. And these are the instruments that we deploy. The CO2 sensor is from Oceanus. It's a pretty new sensor. It has a water impermeable membrane and measures just the gas inside the sensor, measures the CO2. And then this is the IQ that Sandy's in charge of. It measures the flow and the depth in all of our sites. There's different on each site. And so from that we got the flow data. And then this is the YSI. It's just a phone that has different sensors on it for measuring pH, temperature, salinity, a lot of other things that weren't as important for my stuff. And then these are the battery packs that you need to run the IQ and the CO2 sensor. So we deployed the sensors throughout the summer, and then once a month at each site we did sample collection. So we set up for a full tidal cycle, we set up pumps near the sea, and then we ran tubing. It's about 500 feet for some of the sites, all the way back to where we were collecting samples. So we did samples of all sorts of different things. We did greenhouse gases. We collected samples every hour and a half. But the stuff that I was looking at was just the CO2 samples and pH samples. So we collected them in these glass bottles, and then Lang's lab analyzed them for pH and DIC. These instruments get very precise numbers that you can't get from instruments in the field. So it's important so they can be used to correct the data. So this is what I was mostly focusing on, was analyzing the data. I used Python. I used this new environment called Bakari. It runs out of your browser, and it's kind of interesting because kind of nice because you can put all your text files and inputs over here, and then you can call them from the script. I don't know if you guys are familiar with this, but this is just a Python notebook. You can write comments to yourself, and then you can also do code, and the output comes out in the same file, which is useful for just messing around with data. So in this case, I took text files from different instruments, indexed them by date, and then created new files that had a complete data set. and then I did graphing, and so what was really helpful for me in this, interested me too. This is pH analysis that we did. This is the uncorrected pH over a week. This is zoomed into tidal effect, so the green continuous line here is our YSI sensor, and then the red dots are the discrete samples that we got from the lab. And then we did a linear regression, corrected it, and then this is the new corrected data. So we corrected the continuous data to the lab data. So the green line here moves from here to here. This doesn't look that extreme, but this is at Hamlin. At stage, it was more important to correct the pH data. It actually shifted by 0.3. So uncorrected and then corrected. You'll notice this is very noisy, but it didn't end up being that particular stuff. Not really. Not yet. We're still working on figuring that out. We didn't expect it, but that's what we saw. So we're not sure exactly why. So once a month. Okay. No, I don't think so. The bias pretty consistently. Well, we only had a day. So we only had a day at a site. So we had 10 samples from one day. So it's hard to see it as like in a different month, but it would have been recalibrated. And then so the next thing we did was look at PCO2 data. So this is our uncorrected PCO2 from Hamlin. Again, the continuous instrument data. And then we have the lab data, these red dots. This is a comparison. I don't know if you guys have a feel for what CO2 values, but this is microatmospheres of CO2, and the lower estimate of atmospheric CO2 for July 2013 was 397 microatmospheres. So that's like way down here. This is the same graph, but for food stage. And then we corrected the data, we put it on the same, so we've got the sensor data here, and then the lab discrete data here, and the green is Hamlin and the red is stage. We just plotted them together because it's the same sensor that we're just moving around from place to place. This dash line is the one-to-one, and this is the fit line. So you can see that the sensor data tended to be higher, tended to show a higher concentration than the lab data. We aren't quite sure why this is. There's a thought that maybe the equilibrium, the lab makes the assumption that the system is at equilibrium, and the salt marsh might not actually be at equilibrium, so we're not sure which of these numbers is actually right. It could also just be that our sensor measure is really high, so that's not, ProCNS says that's not a normal thing for the sensor. So we're working on trying to figure that out. No, they don't. We haven't sent it back yet. No. We're doing a test right now to see whether that's something that we want to do. They thought that it shouldn't vary by more than like 20 microatmospheres or parts per million. So this is 2,000 off from the lab. So we're looking into that, but for now we did a fit, and the fit wasn't bad. This is R-squared 94 or 0.94. So we can correct this data and use it. It's not just nonsense. It just has a bias. So this is the corrected data for Hamlin and Sage. So you can see so you can correct using one day. We're making an assumption that you can correct for the entire time extension without So we corrected just based on these points for the week. And then we decided to do a test. So we took our CO2 sensor and we put it in a tub of saltwater that we made. And then just to see what it was reading. And then we spiked it with acid, which forced the pH down. And when the pH came down, the CO2 came up, as you would expect, because we had it over here. And we forced it back up this curve. So you see more of it as CO2. We did this just to test our CO2 sensor, see if it was responding normally to a situation that we could predict the outcome. And then we also took discrete samples to analyze in the lab. We don't have those sample results back yet, but we're hoping that with them we'll be able to correct our data better and test out this equilibrium hypothesis to see whether there's anything in it. The green line is pH, and the black line is the CO2. This, we had added some acid, I think, before, too. No, we were still creating the salt water. So we put a bunch of different things in it to make it like ocean water. And it was still coming down off that. And this is where we spiked it. And then we spiked it again over here. So you can see that at the start, the pH was driving it. And then that drives the CO2. And then the CO2 fluxes to the atmosphere and equilibrate. And the CO2 starts coming down, and that makes the pH go back up. And so this is just to get a sense of where we're going with this. I did CO2 flux. We only measured gaseous CO2, not aqueous, but we think that's the larger part of the budget. So this is just CO2 flux in and out of the salt marsh. Here we have the depth of water. I know the scale's weird, but just bear with me. So this is the depth of water. These are high tides at Tinge. And so then we can put the flow data from the I2 on. So you can see that the flow is positive until the high tide, and then it goes negative, as you would expect. There's these strong negative peaks here at low tide, which are kind of interesting features looking at the flux going forward, because the concentration of CO2 is really high at low tide because of the pore water draining. This really CO2-rich pore water drains out and makes a really high concentration. So when we multiply the concentration of CO2 by the flow data to get flux, these peaks that we saw in the flow get exacerbated because they're at low tide. So you get really extreme negative fluxes. So this is going away from the land, going down the axis here. So the negative is export. And then I did the total. So this is the sum of the cumulative sum of the flux data. This is grams over this time period, so total grams. This starting is arbitrary day, July 10th. And then you can see that the flux, when the flux has this strong negative pH, it will step down in the total. And it's always negative in this, over this week here. It's always a net exporter of CO2 laterally. So then I decided to, so the IQ is really cool because it's capable of seeing flow, bidirectional flow, and doing the net flow across the channel. You just put in the stream channel, and it does acoustic ductwork, and you can see that. So then I did, just to get a sense of where we're going forward, I then did a DIC flux just across the tidal effort, and just using the samples that we did, the discrete samples that we collected. So this is the tide, and this is the depth. So it's a high tide, low tide, low tide. and this is the pump thing that you see at stage. And then, so this is the flow data again, just positive, and then SS, which is the negative. And then I interpolated it from 10 discrete PSC samples. I interpolated and multiplied by flux. And this is express flow to get flux here. So you can see follows the flow line really closely because it doesn't vary that much over this tidal cycle. And then I did the net mass of DIC. You can see that it's positive in this case, which is probably just because it's so, we can't really say anything about it as a whole from just one tidal cycle. We need a whole week. That's where we're going in the future. So that our big idea is to take the pH data, continuous pH data that we have corrected from the last slide, take the continuous PCO2 data, which will correct better when we have more results, and then we use these to predict to say what the DSC level is based on this idea here, and then we can multiply the concentration by flow to get flux, a DIC flux, which would be a really interesting kind of unique thing to know continuously for salt marshes. So we haven't done this yet, but so I just like to thank Kevin and Adrian, Sandy, and Wally, who are the guys who I worked with most doing the lateral flux stuff, and then also everyone in our lab, they analyzed all our samples, and then Michael Castro, John Coleman. So those guys were looking at the greenhouse gases, and they were with us on our tidal efforts. And then everyone at Webner, who we're collaborating with on this project, and just for funding me. Yeah, any questions? Yeah.
So one thing that you careful of is that the error in CO2 measurements is in the lateral side.
What did you say, Ty?
The error in CO2 measurements is measuring you be careful of by one direction or other on wetlands now because of now changing flux direction.
Okay.
So there's no relationship there between you guys did some samples on one day.
Yes.
So there's no relationship between the error and the flux direction. Well, but it was close to that one day in the final investigation.
I don't. So this is high tide here in the middle. I don't know that there's a relationship. It looks like they're closer when it's not really changing as much. The back of the lab. It doesn't look like this. Yeah. And in them. This is uncorrected. So then we corrected, and this is, so they fit pretty well then, after you correct. On the whole, yeah. Yeah, but it doesn't seem like there's a difference between flood and ebb here because it kind of it matches best at high tide, but it matches kind of equally poorly when it's rising and when it's falling. So we need a lot more data for this, and it's coming. It reads really fast. Yeah, we did that as part of our subset. We looked at that too and compared it to some other subcavity greenhouse systems that we have, and it read a lot higher, 300 higher. So we're still figuring that out. But they have a special membrane that they claim you can leave out for 3 months at a time without cleaning, and it shouldn't impact the results. So yeah.
one that I had, and then, to be very excited about one of them,
yeah. It has a copper screen, and then it has this special membrane that is supposed to not travel. I think it's yellowish. But I think, it's not like there was a relationship between the continuous data that we got in the lab samples. And the lab samples were taken, so the pump intake was near the CO2 sensor, but it wasn't right on top of it or anything. So I think that maybe speaks to whether it's an accurate representation of the peak as a whole. Approximately. We only have 1 day. Just because we were trying to get that, but because we're taking data from 4 different instruments. Yeah, 1 day. We had 2 days of complete data so far. But yeah, there's gonna be a lot more. But so far we only have 2 days of complete data. So it's really still on there.
One thing that concerned me is that the CPU sensor they have, probably have a range in terms of error. So in other words, they bring their accuracy with precision within 1%, and that's probably only assigned to up to around years. It's very low years. But if you go beyond that, I think the response may be have something to do with error, maybe larger.
Yeah.
More, I don't know.
Yeah.
And I saw the manual, didn't say anything.
Yeah, didn't say
anything. There's a range, but apparently when we compare it with a lot of them, we know a lot of them, we have to compensate that pretty close to the truth. And that's, all down by several hundred maximum, but really 10,000.
Yeah.
I think that there's maybe some manufacturer error.
Yeah. Yeah.
But in terms of volume, if you only apply some days or weeks, I think probably don't have.
Yeah.
Back to the question about
It's the radical.
Yeah. How do you calculate that? Do you have...
I took the microatmospheres of CO2, and then I did the ideal Lateral. So to find the mass, I just used the no. I just did the temperature. I had the pressure times the concentration, right? And so I just took the temperature, and then I got mass over volume, multiplied it by the flow. This scale is not relevant to it.
No, I'm not side.
Oh, okay.
So that I would think that this box is much smaller than the ANC, but this one is much higher than
it's also a much longer period of time. Yes.
The sensor, I don't know what the people talking about
So,